All right, so this week we're going to be looking at the end of chapter 3, which is probably only going to take us about 15 minutes, and the first two sections in chapter 4. Thursday will be a review day, and then Friday will be our last test for term 1. So in 3.7, what they're looking at here is solving systems of equations graphically. So basically that means we're going to be graphing and looking for where two graphs intersect. So it's pretty straightforward. Just remember that in general, a system means that you're solving for more than one variable, generally a minimum of 2. Systems can have more than 2, but not the ones we're doing. Okay, so we're going to focus well, I take that back. We might look at systems that have more than 2 solutions, yeah. But the number of variables we're going to have to solve for is always 2. When you have to start solving for more than 2 variables, like 3 variables, graphing is not a good approach because now you're looking at trying to graph 3-dimensionally and see where things cross. And it's just not the easiest thing to do. So we're going to stick with 2 variables, which means we only have to graph in 2D, and the calculator does that perfect. When you are solving a system with 2 variables, one way you can write your answer is as a coordinate. A system that has 2 variables has an answer that is a coordinate. It's a location. So it's an x value and a y value. Now, some methods that we would use to solve systems if we weren't graphing, we could use substitution. Bless you. We could do elimination. There's other ways we can do it, but the focus of today is on graphing. Since we are graphing, one thing we have to be careful about is the window. Why do you think we have to be careful with the window when we graph something? Yeah?
Because if the window isn't big enough, you won't be able to see where the actual graph is.
Right. So that's the tricky part with graphing. You need to make sure you're seeing everything that's relevant, so you might have to zoom out. Where when you do it algebraically, you don't have to worry about zooming in or out because you're not using a calculator. All right. But that is something we have to make sure we worry about. Also, when you type a problem in on the calculator, what letter has to be by itself on the left-hand side for you to type it in?
Y.
Has to get y by itself. If y is not by itself, we need to fix it. All right, so let's take a look at our first question. So we have 2x plus 3y equals 5, and negative 3x plus 5y equals 21. Okay. Which one of those equations is all set and it's ready to type into the calculator as it is? Neither. Neither one of them is all set. So we got to take both of them and get y by itself. Let's start with this one. Each of them are going to have 2 steps. What's my first step there to get y by itself? Yeah.
Subtract 2x.
Okay, so I'm going to subtract 2x, and I'm going to write it that way because we're getting towards something that's going to be in y equals mx plus b. Okay, these are both going to be lines. So I subtract the 2x, and what would be my last step? Divide everything by 3. Yep. So y equals negative 2/3 x plus 5/3. Okay, so there's my first one. And now my second one. What's my first step to get y by itself in the second one?
Subtract or add 3x to the other side.
Add the 3x. Again, I'm going to write it like a y equals mx plus b. And my last step.
By 5 on each side.
Divide by 5. Okay, so what we're going to end up drawing here are two lines. When you draw two lines that are not parallel, how many times can they cross? Let's say they have different slopes. They can only cross once. Right? Now, if they have the same slope, then that's a special case. There's a couple things that could happen. But different slopes, they are going to cross one time. Okay, so let's graph them and see what we got. Okay, when you type in your slope, one way to do it is like this. Negative 2/3, and then just put the x next to it, plus 5/3. Not the only way to do it, but that's how I'm doing it. And then 3/5 x plus 21/5. I want parentheses around that because there we go. Got it. Now the slope here and the y-intercept, they're not awfully big numbers, so I think a standard window is going to be okay. If I had a y-intercept up in the hundreds or thousands, then yeah, I might have to adjust my window, but I think here you're going to be fine. Okay, so there's the one on the left with the negative slope. The one that's on the right, you're going to see that with the positive slope. And what do I need to find now?
The intersection.
Yeah, so how do we find the intersection on the calculator? Yeah.
Pretty sure it's second calc.
Yep, second
And
calc,
then intersect.
and then intersect. Now, where you put your cursor, it doesn't matter because they only cross one time. So pick any point on the blue, any point on the red, put your guess anywhere you want. All right, so now let's take this. And you could write down the intersection like that. X equals -2, y equals 3. Or what's the other way I said you could write your answer, since it's a location?
Ordered pair.
Yes, you could do an ordered pair. Does the order matter? Of course, that's why it says ordered. There's an order to it. You can't switch them. Okay, so there's your answer to the first one. All right, so there's nothing tricky, nothing hidden. You don't have to zoom out. Lines are only going to cross one time, unless they're parallel, then that could be a special case. Parallel lines could not cross at all, or parallel lines could be the same line, in which case they cross infinitely many times. We're not really looking at the special case in this section. Okay, let's try this one. Yeah?
If lines are always overlapping, does that still make them parallel?
So I guess it depends on how you technically define parallel. I guess when I'm teaching Algebra 1, I define parallel lines as having the same slope and different y-intercepts. So that's how I would define parallel. So same slope, but different y-intercepts. If they're the same slope, same intercept, that's the same line. Yeah.
I have a weird problem with my calculator for some reason. Whenever I try to like do the whole thing that you just did, it gives me an error.
All right, just hit 2. That's not a negative symbol, that's a minus sign.
I see.
Yeah. Okay, let's look at this one. Looking at these two equations, which one of them is ready to type in the way it is?
Both of them.
Both, yep, ready to go. So now, we're just going to put them right in. So make sure when you do negative, that's what just came up, you got to press the button below the 3. Don't press the minus sign unless it's over with the gray buttons, unless you mean subtraction. Okay, so negative x cubed plus 3x squared plus x, and now I do want to do subtraction, so I am using the button on the right side. Okay, minus 3. Okay, negative 2x squared plus 5. All right, I'm going to start with Zoom 6 and see what it looks like. So we're going to get a cubic, and we're going to get a parabola that's been flipped opening down. Now, this one, read the directions, find the number of solutions. You don't have to find them. I just want to know how many there are. So how many solutions are there to this problem?
3.
2 that you can see.
You have to zoom in.
We should, at least, like to me, when I start looking at that one, I can kind of tell, maybe it's just closer. The red and the blue one look like they're getting closer together. So they're probably going to cross. So I need to check that out and see. Let's go to window. I would set the Y min maybe like -35. It's at least going to give you enough of an idea to see if they cross. So we already know we've got 2. And just the question about the third one. Are they going to cross another time?
Yes.
Yeah, even though I can't see it, I can definitely tell they're getting closer. So how many solutions are there to this problem? 3. And if you were going to write down all the solutions, how many numbers would you be writing? 6. Yep, you'd have 3 x values and 3 y values. So that's the part that can be tricky. You might have to zoom way off the screen to see an answer. That one I didn't have to go that far. I would say -35 isn't quite enough. I bet -50. That would probably be plenty. Okay. Any questions on that one? All right, let's try this one. So it says to do it graphically like we've been doing it and algebraically. Let's start with algebraically. What method could I use on this problem if I want to solve it with algebra? Yeah.
Substitution.
Yeah, it's set up perfect for substitution. The bottom equation already has y by itself. So take what the bottom equation tells you y is and plug that into the top equation for the y. So it's set up perfect for substitution. And generally, when we're solving equations that are higher than linear, we try to get what number on one side?
0.
Yes, we try to get 0 on one side. And what would that give me on the right side?
X cubed minus 4x.
X cubed minus 4x. And the reason we get 0 on one side is so we can do what to the right side now? If this was a quadratic, we would have the option of quadratic formula or this. But in this case, we only have the option of this, because it's not a quadratic. Yeah? Factor, exactly. So we're going to factor that right-hand side. It's only 2 terms, so all you can do is pull out a GCF. What does x cubed and -4x have in common? X. So we can factor that out. And now, once you factor that out, you're left with something else that factors. How does x squared minus 4 factor? Yeah.
X plus 2, X minus 2.
Perfect. X plus 2, X minus 2. So now we got to figure out what we would fill in for each of those factors to get 0. I'm just going to make a chart. What could I fill into this first factor to make it 0? 0. How about the second factor?
-2.
-2
2.
and 2. Now, we only have half of an answer there. We have the x's. We still need to get what? The y's. Which formula, because both of these formulas generate y values. You can cube it and then subtract itself, or you can just triple. Which one do you think is simpler? Yeah, I would say just triple each x value. And there's your y values. Okay, so that's how you solve it algebraically. So we don't need anything fancy. Like in chapter 3 earlier, we studied long division, rational root theorem. We don't need any of that. All right, let's graph it and try the same thing. So let's type in x cubed minus x and 3x. Now, I don't need to change my window because I already know the x's and the y values. They're all between 6 and negative 6. So I already have the advantage of knowing the standard window is going to work fine. I'll just find one of them. Let's do second calc intersect. Now, as I find them, is the guess important? Yes, because there's 3 of them, so it's going to give me the one that I put the guess closer to. I'm doing the one in the upper right, which gave me the 0.26. Gave me the last one. You'd have to do that 2 more times to get your other answers. All right. So any question on solving that one algebraically or graphically? Okay, that's really it for 3.7.
If it says to solve graphically, we also have to put the points down also.
Yes, if it says to solve graphically, I'd be looking for all 3 coordinates, or however many there were. Yeah, 1, 2, yeah. Okay. So let's look at chapter 4. So between today and Wednesday, the goal is to do 4.1 and 4.2. And if we needed a little time on Thursday, Thursday's a review day, but I'm hoping we finish everything Wednesday. So what is a rational function? Let me show you an example with numbers first. That's a rational function. Happens to be the simplest one you can have. That's a rational function, not as simple as the first one. That's another rational function. The idea of a rational function is basically it has a polynomial in the top and a polynomial in the bottom. So polynomials are what we studied in chapter 3. The only polynomial you are not allowed in the bottom would be 0, because you can never have 0 in the bottom of a fraction. Okay, so remember when we studied polynomials, polynomials are things that look like this. Something like that. And divide by another polynomial. So that's a cubic polynomial in the top, divided by a linear polynomial in the bottom. Bless you. Things that polynomials cannot have. You can't have negative exponents on your variables. You can't have decimals on your variables, exponents. Okay, so those are 2 really important things. On a polynomial, the exponent on the variable will never be a negative. It'll never be a decimal. You also don't have any imaginary numbers. No imaginaries. Anywhere.
So the exponent will never be a negative and what?
When you have polynomials, the exponents can't be negatives or decimals. You also can't have any imaginary numbers anywhere in the problem.
Any what?
Imaginary.
Okay.
Right, so that's an example of a polynomial. That's another example. That's a quadratic divided by a linear. Notice there's no negatives on the exponent, no negative exponents, no decimal exponents, no imaginary numbers. Okay, there's another one. That's a quadratic divided by a quadratic. But that's a polynomial in the top. The bottom is a polynomial. And when you divide two polynomials, we call it a rational function. Right, any question on what a rational function is? Remember, you just can't have 0 in the bottom. And what we're going to do with rational functions this week is focus mostly on how they look when you draw them. 4.3 we're going to do next week. That's solving them. But this week is mostly going to just be sketching them. So, what is the domain of a rational function? Well, rational function means you have a fraction. What's the only thing that you are not allowed to do in a fraction?
Divide by 0.
You can't divide by 0. So the domain is every value except numbers that would make the denominator 0. It is possible that there are no numbers that would make the bottom 0. Look at this one. Say x squared minus 5 over x squared plus 1. How come there's no real number you could plug in to make the bottom 0 there? Yep.
Because if you put in -1, it would just automatically be 1. Because -1 plus 1 is 0. But if you square -1, then it's 1. So then 1 plus 1 is 2.
Is 2. Okay, so we know -1 doesn't work. How come there's no number that would work? You could try real numbers all day and you'd never find one that works. Yeah.
Because the square negatives will always come out to positives. If you plug in a negative for the x.
Okay, so yeah, if you square anything here, it's going to be either 0 or higher.
And if it's 0, it'll add 1. So
Yeah.
it can't be 0.
If you take something that's 0 or higher and you add 1 to it, you're never going to get 0. The only thing you could plug in would be I, because I squared is -1, and -1 plus 1 is 0. So this kind of problem, the domain is all real numbers. There is no number you could plug in to make the denominator 0. Let's look at one that does have a number. That would make it 0. Okay. So to find the domain, what I generally do first is find the number that would make the bottom 0, and then write down not to use that number. Okay. What number would make the bottom 0? 3. So think of it in two sections. You can use anything going this way. You can use anything going this way. You just can't use 3. So how would we write all the numbers that are lower than 3?
And then negative
Comma.
3 with the same symbol as the infinities.
Okay, so negative infinity to 3, not including 3.
And then not including 3 to positive infinity.
And open interval from 3 to infinity. That's how you'd write the domain in this problem. Generally, when you have one number you need to exclude from the domain, you have to write 2 intervals. Excluding one number means you write 2 intervals. It's like taking a strip of paper and cutting it once. You get 2 pieces. All right, let's try this one. So the numerator doesn't really play a big part here in terms of the domain. You're just trying to find what would make the bottom 0. What would make the bottom 0 this time?
2 and negative 4.
2 and negative 4. So now it's like you have a strip of paper and you cut it twice. How many sections does that give you?
3.
Gives you 3 sections. Anything below there, between there and there, or above there? So how would we write the, we'll call it section 1? Yeah.
So is that a 7 or a 1?
Negative
No,
4.
no, in the equation.
Oh, up here?
Yep.
That's a 7. 7x squared. So how would we write section 1? Yeah, go ahead, Maggie.
Parenthesis, negative infinity, and then negative 4 with a parenthesis around it.
So that represents all the numbers below negative 4. Or, what's my next section? Yeah. Oh.
Parenthesis, negative 4, parenthesis, 2.
2. Perfect. So, yep. Exactly what Shelby just said, negative 4 to 2, open parenthesis on each end because you can't include either number. Or, what would be my final interval? Yeah?
Parentheses 2.
Parenthesis what?
2.
2?
Comma infinity.
Yep. I didn't have enough space or something. No. Thought I had plenty of space. So 2 to infinity. So when you have 2 numbers you can't use in the domain, you have to write 3 intervals. And generally that's as many as we do. Any question on that one? All right. Now let's try this one. It's similar to example C. I just changed the order I did them in. But what are we going to have to do with the denominator first? Because the way that that's written, that's hard to figure out the zeros. We have to factor it. So if you're trying to find a denominator and it's not, and you're trying to find the roots and the denominator is not factored, that's your first step. For what we're doing, the numerator doesn't matter. Does it matter for other things? Oh yeah, but not for this, which is why I'm not even focused on it. Okay, so we'll have an x and an x. What about my signs?
Negative and negative.
Nope, they can't be negative, negative. That wouldn't give us negative 2.
Negative, positive.
Right, we're going to have a negative and a positive. Because a negative times a positive is a negative. And 2 numbers that multiply to give me 2. And I would put them 1 and 2. If we check it, that's x squared plus 2x minus 1x. That's 1x. Perfect. So now, what are the 2 numbers that we are not allowed to use? Yeah?
1 or negative 2.
1 and negative 2. So I just put those off to the side. And now think of my intervals. We can go below negative 2. We can go between negative 2 and 1. Or we can go higher than 1. So for some, it kind of helps to just do it on a number line so you can see, like I did here, and label the sections. Or if you can do it like that, that's fine too. That's my domain. Okay. So any question on finding the domain? Now, this problem could have been a lot more annoying. What if this wasn't factorable and you had to find the zeros of the bottom? What would you have to do now? Yeah?
Quadratic formula.
Yes, you'd have to do quadratic formula and get your answers. And they would look as nice, because if you can't factor it, you're not going to get nice numbers. So you could get something like 3 plus or minus root 7 over 6. Okay? It doesn't matter what kind of answers you get. The pattern that a quadratic denominator will always follow is it's always negative infinity to some lower number. Then it's the lower number to the higher number. And then it's the higher number to infinity. That's always the pattern when you have to exclude three things. You just have to solve for the lower number and the higher number. If it's factorable, that makes finding the L and the H easy. If it's not, you're going to have to find the low and the high by quadratic formula. So that's the pattern when you have two values that need to be excluded. The pattern when you have to have one value excluded is just negative infinity to that value, and then that value to infinity. There's no low and high. It's just one number. 3 in that case. Any questions on that? All right. So those functions we just looked at are what we call rational functions. They definitely weren't the simplest rational function. That's the simplest rational function. Okay, so the simplest rational function is the function 1 over x. Okay, and that is called the reciprocal function. So let's graph that and see what it looks like. Okay, when we graph that, the calculator is going to do part of it fine. It's going to do a good job with it. And then there's another part it's going to graph that it doesn't. Let's look at that. Okay, so that's the graph of the rational function. Does anyone have a guess what part of that I think is not really drawn well? Yeah?
Part approaching 0?
Yeah, as you start to approach 0, okay, the graph curves up and down very sharply because 0 is not in the domain. So when you approach a value that is not in the domain, that's one thing that can happen. It can start to curve up and down sharply. But it shouldn't look like it's just stopping. It should look like it's going to keep going up like that and down like that. I think the left and the right looked fine. It's just more the up and the down. Okay, so that's called the reciprocal function. 1 over x. Now, I want to look at two things. Remember, the arrow means approaches. So I want to look at what happens, not as we approach like the middle, but as we head in opposite directions. As we head to infinity and negative infinity. What does it look like is happening to the y value? If you trace along this blue curve and keep going to the right forever, what does it look like your y value is getting very close to?
0.
It's getting very close to 0. But remember the formula that it came from. If I take 1 and divide by even 1,000,000, is that 0? No, it's very small. It's getting close to 0, but it will never reach 0. How about going the other way? If I take 1 and I divide by negative 10,000,000, am I going to reach 0? No. I'm going to have a very, very small negative number. Just like when I head to the right, it's a very small positive number. So what this is saying is as you head to the right and to the left, your y value is approaching but never reaching 0. So really what we have in here is this, it's kind of like thin, I usually do it as a dotted line. like that. That dotted line represents something that we're going to curve down to, but we never reach. Or on the left, we're curving up to it. Does anybody know what you call that kind of line? The dotted line that you get close to but never reach. Begins with an A. Yeah?
Asymptote.
That's an asymptote. Yep. That's an asymptote. So in this problem, if you draw in the y equals 0, which is the equation of the x-axis, that is a horizontal asymptote. So it's that dotted red line. The way that you find a horizontal asymptote, if you're looking at a graph, you zoom out and you look at the left and the right ends, and you ask yourself, does it look like my graph is getting close to something? If you don't have a graph and all you have is a formula, the equivalent to looking very far left and right is letting the x value get really big. Okay? Either a really big positive or a really big negative. Either way. And you take that really big x value, I usually just use like 1,000,000 in my head as kind of as a gauge. Plug in 1,000,000 for x and tell me what's going to happen when I do that. Whatever's happening, that number that I'm getting close to, that's my horizontal asymptote. Okay, so there's a couple pictures of horizontal asymptotes. Notice in the definition, I never said anything that you can't cross it. I never said you can cross a horizontal asymptote. But the idea is, as you continue to head to the right or the left, you start getting closer to it. But it's very possible you cross it early on, and then as you continue, you don't end up crossing it again. That's fine. Okay, so those are both examples of horizontal asymptotes. And that's an example of one up there as well. Okay, so any question on the idea of what a horizontal asymptote is? It's one of the important asymptotes that comes up in this section. Horizontal, and then there's another one we'll do in a minute. Okay, so this one they want me to find the horizontal asymptote. Okay, so the first thing to make sure we get right, because there's no guesswork with this part, is when you write the equation of a horizontal line, that's a special case, because it's not on a slant. Okay, it's not y equals mx plus b. What letter is always by itself when you write the equation of a horizontal line? Yep.
X.
So when you put x by itself, that's going to be vertical.
So what?
So it's going to be y. The difference is there is no mx. There's no mx in a horizontal line. It's just y equals, and then it's just a number. Okay, so I don't have a picture of this one, okay, and I don't really want to do a picture. So I want to find the horizontal asymptote. So let the x value get really big and tell me what's going to happen. If it's too difficult to figure out what happens to the whole thing, then break it down and start with what's going to happen to this. In this fraction, as x gets bigger and bigger, what happens to the bottom of that fraction? Just the bottom. It gets bigger. As x gets bigger, the bottom of the fraction gets bigger. What happens to the whole fraction if the bottom is getting bigger? It gets smaller. In fact, what's inside this box is going to get so small, it's going to approach what? 0. That part is basically going to turn into 0. When x is 10 million, 1 divided by 10 million, it almost doesn't even matter. It's so small. So this part's going to get close to 0. What do you get if you take something that's extremely close to 0 and then add 2 to it?
Just out to.
You basically are going to get something extremely close to 2. Might be like 2.000001. It's very small. So that is your horizontal asymptote. Basically, anything that has an x in the bottom of a fraction is going to make the fraction just disappear. If you have an x in the top of a fraction, that's different. We'll talk about that some other time. All right, let's try this one. So same direction. Find the horizontal asymptote. Since it's horizontal, what letter will be by itself? Y. And now, as x gets bigger and bigger and bigger, what's going to happen to what I just put a red box around? It's going to get very small, and it's going to get close to 0. If you take something that's close to 0 and subtract 3 from it, what do you get? Very close to -3. Okay, so the horizontal asymptote there is y equals -3. And you could always, you could double check it. Type that in, go to your table. And now pick a big number for x. Pick like 50. -2.98. Go even bigger. Go 600. -2.998. Okay, let's do like 2,000. -2.9995. It's getting very close to -3 as x gets bigger and bigger. And this is getting close to -3, but it's just a little bit above -3. Okay, think on the y-axis. We have -3, -2.9. Yeah, that's just above -3. If you go on the other side, it's just below -3, -3.0001. But still getting close to -3. Now, eventually, if I type in something like, let's type in 99, just a huge number. So it tells me -3. But is it really -3? No. If I highlight it, it's very close to -3. And eventually, it'll run out of decimals here too, and it'll just say -3. But it's not. So I just showed you guys the graph. Well, I didn't show you that one. I did the other one. Did anybody want to see that one? Yeah? Just see what it looks like? So when you graph that one, it's going to be the same thing, but it's going to be a +2. As you head left and right, your graph should be getting very close to +2. Yeah?
Can you use the bathroom real quick?
Yeah. If you go to your table, notice if you type in pretty big numbers for x, it gets very close to +2, but it never quite reaches it. And this one, remember, that's not +2. Now, this one's not close to 2 at all, 0.5. That's because 0.5 isn't a big number. What we're doing right now only works if you plug in a big number for x, not a small number like 0.5. That's not going to help. Okay, so big numbers, hundreds, thousands, millions. Okay. Now, instead of looking what happens as we continue to head to really big numbers, now I do want to look at what happens as we go to a small number. And the small number I want to look at is the number that would cause you to do something in this fraction you're not allowed to do. What number could you plug in for x and it would give you an error in your table? 0. Okay. So what I want to do is look at what happens as we approach the number 0. So let's just graph it and see what it looks like. 1 divided, actually we don't even need to see what it looks like. Let's just use the table. Now let's pick a number that's very close to 0. You can't use 0 because that's an error. But what's a number that's really close to 0? Yeah?
0.0001.
0.0001. That's extremely close. Look at your y value. 10,000. So we are up very, very high. What's another number that's very close to 0, but on the other side? So that's on the positive side. Yeah?
-0.0001.
Yeah, negative 0.0001. So on the other side, we're at negative 10,000. So the way we can summarize what just happened is as x approaches 0 from the positive side. That's what this means. What I just circled in red is that whole thing I underlined in red. As x approaches 0 from the positive side. This little symbol after the 0 means positive side, because there's always two ways you can approach a number from: the right side and the left side. This is the positive side. This is the negative side. This is approaching from the positive side. So approaching from the positive means you're heading to the left. Approaching from the negative side means you're coming from the negative towards 0. You're coming from the right. Coming from the right side. Or left side, heading to the right. So the positive side is over here. The negative side is over here. And this is the notation you use to describe which side you want to come from. The positive side or the negative side. And we saw that when we plugged in a value very close to 0 on the positive side, it went up very high. On the negative side, it went down very low. Now, does anybody know what that indicates? When you start to approach a number, and it goes up very high, and it goes down very low. That means you have something in your graph similar to what we just talked about, but it's it's the other one. Yeah?
A vertical asymptote?
Right. This behavior means you have a vertical asymptote. So anytime you start to get close to a number, if your graph curves up to infinity or down to negative infinity, that's a vertical asymptote. What else? Vertical asymptote is always written with an x by itself on the left. Okay, so on the test, if I ask you for the equation of a vertical asymptote and you put y equals, it's got to be x equals. Y equals would be what? That's horizontal. Yeah. So how do you find the how do you find the vertical asymptote? Well, if you can find the domain, then you can find the vertical asymptote. It's the same steps. But this is what it'll look like graphically. If that number is a vertical asymptote, then as you approach that number from either the left or the right, all of a sudden your graph is either going to curve up or it's going to curve down. It's going to do one of those two things. But it'll always have this slope. And we'll say that dotted line is at some number. We don't know, whatever number it is. So that's all that this means. Your graph curves up and down as you approach that number. So how do you find that number? All you have to do is figure out what would cause you to divide by 0? That's how you find vertical asymptotes, which is the same thing you do when you're finding domain. Figure out what would cause you to divide by 0. The difference is when we figure out what causes us to divide by 0 when we're doing domain, we say don't use those numbers. When we figure out what causes us to divide by 0 here, we say use that number. That is the vertical asymptote. So let me type in x plus 5 divided by x minus 2. What do you think the vertical asymptote would be in this problem? 2, because that's the number that as you get close to it, it would cause you to divide by 0. So watch what happens as we get close to 2 on the x-axis. All of a sudden my graph curves down and it curves up. What if I did something like x minus 4? What do you think the vertical asymptote would be now? 4. Okay, so watch what happens as you get close to 4. Vertical asymptote, right at 4. Now, let's look at this one. What number could you plug into the bottom and you divide by 0? But what happens when you plug -5 into the top?
It cancels out.
So when you plug -5 into the top, it gives you 0. When you plug -5 into the bottom, it gives you 0. Well, that's a problem. That would not be a vertical asymptote at -5. To be a vertical asymptote, it has to make the bottom and only the bottom 0. So -5 is a number we can't plug in. And I'm surprised. It actually kind of drew it exactly like it should have. I've never seen that before. What does it look like happened at -5? There's a hole in it. I've never seen it do that before. There's a hole in the graph. So when you have a common factor in the top and in the bottom, like that, x plus 5 over x plus 5, you will not have a vertical asymptote. You will have what's called a hole. Now, if you just change it a little bit, make the top 5.1. Now, -5 does not make the top 0. And now you'll see a vertical asymptote. I had kind of a hard time sketching it, but there is a vertical asymptote there now. All right, so as long as you don't have any common factors in the top and in the bottom, you will get vertical asymptotes where the denominator is 0. If you do have a common factor, you will get a hole. Okay, you'll get that little gap in the graph, just like that. Okay, but that's a very specific circumstance to get a hole. You have to have common factors. Here's another one with common factors. You would not get a vertical asymptote at -2 in that graph, because there's a common factor of x plus 2 in the top and the bottom. You'd get a hole in the graph. And usually you can't see the hole. Like I said, I've never seen it be able to draw it the right way. Must be just the exact problem I used and numbers, I don't know. All right, so let's try finding a couple vertical asymptotes. Okay, so first thing I want to check for is common factors. Are there any common factors in the top and the bottom? Right there. No. To have a common factor, you need an x minus 2 in the top and an x minus 2 in the bottom. We don't have that. So that means whatever makes the bottom 0 will be a vertical asymptote. Okay. What value makes the denominator 0? 2. And because it's a vertical asymptote, what letter goes by itself on the left? X equals 2. That's it. That's the vertical asymptote. All right, let's try this one. How about 1 divided by x plus 3 minus 1? Are there any common factors in the top and in the bottom right there? No. If there was a common factor, we'd have an x plus 3 in both. What would make the denominator 0?
-3.
-3. That's your vertical asymptote. Now what if I did this? Minus 12. What would make the denominator 0 now?
Still -3.
Still -3.
Just moving up and down.
Yeah, this just moves it up and down. When you have something that's a vertical line, moving it up and down doesn't change it. This number affects the vertical asymptote. This number affects the horizontal. They're totally separate. Any question on that one? All right. Graph that. Mixture problem I'm probably going to do tomorrow because I'm going to finish up with something else. Transformations. So I started to touch on the transformations a little bit when I tried to explain which number is going to affect wherever it was, which asymptote, right here. So there's 4 different numbers we can have. Shifting up and down, shifting left and right, stretching up and down, stretching left and right. So I'm going to make a diagram that shows you what each number is and where it would be. So there's 2 ways we can write it. We could write it, let's see, like this. So you could see it like that, or you could see it with the C in front and a 1 in the top. It's still the same thing. Plus or minus D. Okay, I'm just going to label the diagram on the right, but all the labels apply to the one on the left. When I say inside the denominator, I mean what's in that red box. Okay? Anything that is inside the denominator is your horizontals. A is a horizontal shift. Now, if we remember a little bit about horizontal shifts, when you have plus a number, which way does plus make your graph move? To the left. Okay, with a horizontal shift, it's backwards. Plus is going to move it to the left. Minus is to the right. Now B is also horizontal, but it's not a shift. It's multiplication. B times X. Does anybody remember what kind of transformation multiplication is? It's not a shift. It's a stretch. So that's a horizontal stretch. And it is also backwards. So let's say you had something like 1 over 3x. The bigger you make B, the more compressed it gets. So if I was going to describe this one, I would say horizontal stretch by factor of 1/3. The bigger you make this number, the more squished it gets. If you make that number a 5, it would be horizontal stretch by 1/5. The bigger the number, the more squished. The smaller the number, the more stretched. So if you had something like, I'll just do another example, 1 over 1/2 x. That's a small number. That stretches your graph bigger. Small numbers make it bigger. It's the opposite. So this would be horizontal stretch by factor of 2. I know it's weird, it's how it is. It's a small number, so it stretches it bigger. Okay, so A and B are the backwards ones. C and D are not. C and D are on the outside of the red box. So which direction do you think both C and D are going to affect? Yeah, these are your verticals. So C is on the outside, and it's multiplication. So that's going to be a vertical stretch. Any multiplication is a stretch. Any adding or subtracting is a shift. So it's multiplication on the outside. That's a stretch. And there's really nothing special to say. If you have a bigger number, it stretches it bigger. A small number will compress it smaller. And sometimes you'll see the C and the 1 multiplied together, and they'll just put it in the top. So having something like this is the same as having this. These both have a C value of 3. It's just 2 different ways of writing it. Okay, and what about D?
Vertical shift.
It's on the outside, and it's adding or subtracting, so it's a vertical shift. Positive would move it which way?
Right. Left.
What kind of shift is it?
Oh, wait, vertical.
Vertical.
Oh.
Up.
Up.
Yeah, wrong direction. Vertical would move it up, and negative,
Down.
down. Now, what about if B is negative? What does a negative generally cause the graph to do? Yeah, it's a flip. Can you be more specific over which axis?
B would be over the y-axis.
Let's see. If B is negative, B is a horizontal, so it would flip. It's a horizontal reflection,
Y-axis.
which is over the y-axis. Because B is a horizontal reflection, because it's with the horizontal stuff. How about if C is negative? What was it? That's a vertical reflection, and when you reflect something up to down, that's over the x-axis. Okay, so that basically covers everything you need to know about transformations, as long as you can identify the A, B, C, and D. And they are done in that order. Okay, so now let's try one and see if we can do it. Okay, so it says to find the asymptotes and describe the transformations. Well, let's start with the transformations. Does what's in green look like, try to see if I can get that thing back up. Does it look like the pattern that I showed you? What do you think? Does it look like it's set up where you can see the A, the B, and the C, and the D clearly? No. To see those, you're either supposed to have a 1 in the top or just a single number in the top, not a number with a letter plus or minus a number. You're not supposed to, that's too complicated to look at. So what we're going to do is we're going to fix that. Okay, we have to rewrite this so it looks more like that. So to rewrite it, let's do that out. Let's divide those two things. So I'm going to put 5 on the outside, and I'm going to do synthetic division. What numbers would go on the inside?
2 and negative 13.
2 and negative 13. And all I'm doing is I'm going to divide this out so I get something that looks nice. Remember how you can write your answer. Quotient plus remainder over divisor. Okay, that's how you write your answer when you do long division. And then you're going to have something that looks just like that. Okay, bring down the 2. What's 5 times 2? 10? What's negative 10? What's negative 13 plus 10?
Negative 30.
Okay, and we're done. That's all there is to divide. What's my quotient there? 2. Remember, this is your quotient. And this number over here? Remainder. So my quotient is 2 plus, well, my remainder is a negative, so it's going to be minus. My remainder was 3. And what was my divisor?
2x minus 13. 4x minus.
That's my 2x minus 13, that's my dividend, that's my numerator.
35.
X minus 5.
X minus 5 is my divisor. That and that are exactly the same thing. But the one on the right, even if, I think if I did this, you'd see it even better. Negative 3 over x minus 5 plus 2. Now we can identify the A, the B, the C, and the D. Let's start with the first transformation. Is there a number in the A spot in this problem?
Yes.
Yes. What is that number?
Negative 5.
That's a negative 5. So that's going to shift my graph to the right. How many units?
5.
Perfect. Shift right 5. Okay. Is there a number in the B spot?
Yes. No.
Well, there's a number there, but it's a 1, so yeah, it doesn't do anything. Okay. Let's go to the C spot. Is there a number there?
Yeah.
What's the number?
3.
3. Wait, what's the number again?
3. 3.
3. Right. If it's a negative, we talk about that separate.
Right, that'd be part of this. Alright.
So C is a what?
Oh,
And what does it do?
factor of 1/3.
It's a vertical stretch.
Vertical stretch by factor of how much?
That'd be 3.
3. Remember, the vertical, there's nothing backwards about it. That's why I didn't write a huge explanation there. Just vertical stretch by factor of the number. Now, we also said the C is a negative. Yes, there's a negative. So what does the negative cause it to do?
Flip over the x-axis.
So that's going to flip over x-axis. And is there a number in the spot for D?
Yes.
Yes, there is. We couldn't really see that the way it was written in green, but in black we can. What's the number in the spot for D?
2.
2. And what's that going to do?
Shift it up to.
Yep. Shift up 2. Okay. And last thing they want is the asymptotes. I would look at the version in black. Look at the part I just circled right here. As x gets bigger and bigger, what's going to happen to the bottom of this fraction? It's going to get bigger. What's 3 divided by something that's getting bigger? Very small, getting close to what? 0. And what's 2? Take away basically 0.
2.
2. So that's your horizontal asymptote. Okay. Vertical asymptote, that could look at the green one or the black one, it doesn't matter. What causes you to divide by 0? 5. Yep. So I think the asymptotes are pretty easy, but the transformations, those are a little tricky unless you do out the division. You don't always have to do division. It's only because this one wasn't set up right. Um, 48A and B, we're going to come back to that one. That's a mixture problem. We'll do that tomorrow. Okay, we only have half a section planned for tomorrow and half a section on Wednesday and a review day Thursday, so we got plenty of time. So 8 through 10, that's solving systems by graphing. And page 222, that's on finding horizontal and vertical asymptotes and describing transformations. 48A and B, that'll be the first question on tomorrow.